Hello, and welcome to Lesson 17 of this Introduction to Calculus with Wolfram U. The topic for this lesson is the mean value theorem. So let's begin with a brief overview of the lesson. So the mean value theorem, roughly speaking, relates the slope of an interval with the instantaneous slope of some point in the interval. Now, let's look at that a little bit more in detail. So here I've got a curve, and I join the two endpoints over here by a secant. And what the theorem is saying is that the slope of this interval over here is somehow related to the slope of this tangent at some point. So that's what the theorem is about the slopes of intervals and the slopes of tangents. So the goal of this lesson is to first of all understand the mean value theorem and then give a few applications of the theorem. But we'll begin with a special case of the theorem called Rolle's theorem. So as a motivation for Rolle's theorem, let's look at the function f of x equal to x squared. So here is a plot of the function of the parabola. And notice that the value of the function at the two endpoints, -2 and 2, is the same. And the slope at 0, the derivative, is 0. So that's the hint for Rolle's theorem, that the slope is 0 at the top, and you also have a tangent, so to speak, at which the slope is 0. So now a more formal statement of Rolle's theorem, which was proved by Michel Rolle. And what it says is that if you have a function that satisfies three hypotheses, first of all, it is continuous on a certain closed interval, it is differentiable on an open interval, and the value of the function at the left endpoint is the same as the value at the right endpoint, then there is a number c in the interval at which the derivative becomes 0. So the previous function I talked about, in fact, satisfies all the three hypotheses. After all, you do have a continuous function, it's differentiable, and the values at both the endpoints are the same. So here's a plot which just confirms the theorem and says that the slope of this secant line is the same as the slope of that tangent over there, which is 0. Okay, so now on to the problems with Rolle's theorem and how you apply it. So first of all, let's look at 1 over x squared on the interval -1 to 1. And notice that it has a discontinuity at 0. So, of course, it's not differentiable over there as well. Now, the values at the endpoints are certainly equal. However, it does not satisfy all the hypothesis of Rolle's theorem, and hence we cannot guarantee that there is any number in this range at which the slope is 0. In fact, you can confirm that using solve, and you check that the derivative is never 0 in this interval. As another issue with the theorem, let's look at the absolute value function between -1 and 1. Now, clearly, that is continuous, but it is not differentiable at x equal to 0. There's a corner at x equal to 0. Now, the value of the function at both endpoints is the same, but since it does not satisfy all the hypothesis of Rolle's theorem, therefore you cannot guarantee that there is a number at which the slope is 0. And once again, you can use solve to confirm that there is no such value. So that's the derivative of the absolute value function on the interval, and it's never 0 on that interval. Okay, so now on to the mean value theorem and some motivation. So in the earlier example, we said that the secant line between -2 and 2 and the tangent line at 0 have the same slope. Now, the whole situation is very symmetrical. So what we do is we make it slightly less symmetrical by looking at the interval -0.5 to 1. So that's the interval over here. And now you notice that the secant line at x equal to negative 0.5 and x equal to 1, the line joining those 2 points has got slope 1/2. You can calculate that. And the same thing happens at x equal to a quarter, namely the tangent line at that point has a slope of 1/2. So the mean value theorem is just a modification, a more general version of Rolle's theorem. So here is a formal statement of the theorem which says that suppose you have a function f that is continuous on a closed interval, differentiable on the open interval, in that case, then there is a number c in the interval at which the slope of the tangent line equals the slope of the secant line joining the endpoints. So more formally, f prime at c is equal to f of b minus f of a over b minus a, and sometimes it's easier to cross multiply and get the same equation in a slightly different form like it's written over here. Now, of course, Rolle's theorem follows from the mean value theorem, because if you set f of b equal to f of a, then you have f prime c equal to 0 at the point c. So that's the Rolle's theorem for the sine function on the interval 0 to pi. So there are some issues with the mean value theorem and how you interpret it. So for example, you could have more than one c which satisfy the theorem. So here you have a curve in which that's the secant line, and those two tangents have got the same slope as the secant line. And in fact, if you have a constant function like f equal to 5, then the slope is 0 everywhere. So here's the constant function 5, and if you plot the function derivative, you see that the theorem is satisfied everywhere. So you have some exceptions to the mean value theorem when you have either more than one value, or you might even have infinitely many values, because if the slope happens to be 0, then the function must be a constant. Okay, so with that, some applications. So the first application, let's look at the function x cubed minus 8x on the interval 0 to 4. And you want to find a c in the range which has a tangent line parallel to the secant line to the endpoints. So the first step, you note that the mean value theorem is certainly applicable because you have a polynomial function. So you solve for c, for x, like in this equation, and the value of c, or x, is 4 over square root of 3. So at that value of x, we actually have a tangent line that is parallel to the secant line through the two endpoints. So now let's check that with the tangent line and a plot of the curve and tangent line. You can see that the secant line over here has the same slope as the tangent line over there. Okay, so as another example of the mean value theorem, let's talk about a function f whose value at 0 is 4 and whose derivative is bounded above by 6. And the question is, how large can the value of f at 3 possibly be? Now, because f is differentiable, therefore clearly it is continuous. And so what we'll do is we'll apply the mean value theorem on the interval 0 to 3. Now, the mean value theorem says that you have the equation f of 3 minus f of 0 is the value of the derivative at that point c times 3 minus 0. So you have a c with that property. Now, because you have f prime less than or equal to 6, therefore you set up the equation which puts f prime c to be at most 6, and you solve it for f of 3, and you find that the value of f at 3 can be at the most 22. Okay, as another example, let's try and show that this polynomial x cubed plus 8x minus 2 has exactly one root. Now, because the function is continuous, so you can apply the intermediate value theorem to try and show that a root exists. So the point is that the value of f at 0 is negative and the value at 1 is positive. So the function must take every value between those two values. So at some point or other, it must become 0. So you certainly have a root in the interval 0 to 1. Now, let's suppose there are two roots, a and b. Then the mean value theorem would say that you actually have a slope of 0 between them, and hence you have a point C for which the slope is 0 as well. But then if you look at the derivative, it's 3x squared plus 8, which can never be 0. So it's clear that you only have one root. But let's just plot the function and make sure. So you see over here that the function becomes 0 somewhere to the right of 0, but then never again. Now, as an amusing application of the mean value theorem, let's talk about speed limits. So suppose you got 2 points A and B on a road, and they are 90 miles apart. You start from point A at noon. And suppose you don't take any breaks in your journey, and you get to the point B at 1 o'clock. Now, the speed limit in that area says that you cannot exceed 80 miles per hour. The question is, should you receive a speeding ticket or not? Well, here's the average speed for the whole trip. It's 90. So if you apply the mean value theorem, at some point you must surely have crossed the speed limit of 80 miles per hour. So certainly you should receive a speeding ticket, and it's going to cost you some money. Okay, so let's summarize the lesson for today. And we saw that the mean value theorem relates the average slope of an interval with the instantaneous slope in the interval. So basically it says that you got a point at which the average slope is the same as the instantaneous slope. And of course, this theorem is a very useful theorem. We saw some applications, but in the next lesson, we'll see even more, where we'll talk about the graphs of functions. That's really a very interesting geometrical problem which gets solved nicely with the use of the mean value theorem and other properties of derivatives. But before you do that, do look over today's lesson, do review the exercise, and be ready for the lesson on graphs of functions. So I'll stop over here. Thank you.